Okay, so we have the vowels. Now let's look at the consonants. Because consonants involve more substantial constrictions, they often have acoustic properties beyond just the formants that we need to watch for. But the formants are almost always part of the story too. So where are we going to start? Let's start with the approximants. And we'll start with the central approximants. We'll talk about laterals a little bit later. So here's two utterances, ee and uwu. Start by looking at the waveform. One of the things we notice is that as we go from the vowel into the approximant and then into the vowel, approximant, vowel, the approximant has less energy. And this makes sense, right? We have more constriction, so less acoustic energy is getting through, more is getting absorbed along the way. So that's the first thing that we notice. If we look at the spectrogram of these same sounds, you see a little bit of that dip in energy, but along the way the formants are fairly consistent. It's hard to tell here because the energy drops off so much that some of the formants kind of disappear, but really the formants don't change a lot. And this is because those approximants, the y is very close in terms of where the tongue is to the e vowel, and the w, the w approximant, is very close to the u vowel. And so aside from that dip in energy, not a lot is changing. Okay, now the other central approximant that we have in English is the r sound, that alveolar approximant. Now it doesn't have a vowel that's right next to it, so we can't put it next to a vowel and say, hey, look how similar it is, but r is very distinctive acoustically among all the sounds of English because it has a very, very low F3. So when you say ara, the real big difference is that F3 diving down and sort of smashing into F2 there and then coming back out after the R sound. So that's the big acoustic giveaway for the R. And there's also an overall a loss of energy, a drop in energy during the approximant relative to the vowels, like we saw in the other approximants. Okay, so that's the central approximants. And now let's look at some fricatives. So acoustically, the main thing about fricatives is all of that turbulent airflow that's generated wherever the constriction is, right? You've got this narrow opening and air is flowing through, so it's getting all turbulent. And we can tell different fricatives apart from each other by the spectrum of the friction noise, that's how the energy is distributed, the overall amplitude of that noise, its duration, and some aspects of the transition into and out of the neighboring sounds. So for the spectrum, the textbook goes into detail about half wavelength and quarter length resonators and calculating different formants, and this is all very, very cool, definitely worth diving into in principle. But in this course, I'm going to focus on the outcome. We learned, for example, that the alveolar fricatives have a concentration of energy, a prominent formant, around 4,500 hertz and above. On the other hand, the post-alveolar fricatives concentrate their energy lower with a formant around 2,500 to 3,500 hertz. So let's quickly have a look at those two formants. So on the left we have a sa, and you see this high energy formant. This spectrogram frequency range, I've put it, instead of up to 5,000 as usual, it's up to 10,000 because fricatives tend to have energy, interesting energy stuff happening a lot higher than for the formants of vowels and other sounds. So for this S, you see the energy starting around 4,000 hertz, and then it's quite high after that. Whereas for the sh, the prominent energy starts lower, closer to 2,000 or 2,500 hertz. Okay, so that's distinguishing those sounds. And then we also have a different class of sound, class of fricatives. Here we have the bilabial, the dental, and the glottal, a fa, a tha, and a ha. Now the first thing to notice is that there's a lot less energy. You see how much energy there is in this S relative to the vowels on either side, and even the esh is similar in energy. But if we move here, the energy gets a little bit less. The vowels are more prominent relative to the fricatives. And this, of course, varies from utterance to utterance. Also, this energy is fair. It's not showing a big concentration in these lower frequencies like the other ones did. Another thing to notice about the H, notice how H, although it's voiceless, it carries through a lot of this formant energy from the vowels. Now, remember that although we're talking about fricatives, consonants, not vowels, we still have the same space. And with the H, the friction energy is being produced at exactly the same place where voicing would be produced for a vowel. And all the space above that is free to resonate just as it would for the vowel. So when I say aha, for the H, all I'm doing is changing what's happening in the glottis, and everything else is positioned as for a vowel, and so it's going to resonate as for a vowel. And so when we look at that spectrogram on the right, the H is basically just a voiceless, or sometimes called whispered vowel, whispered because you have that friction being generated at the glottis, like it is for whispered speech. Okay, so we have on the one hand the s and the sh that have a lot of energy. Those are the sibilant or strong fricatives, and on the other hand we have all these other ones that don't have quite so much energy, mainly because the turbulent air, just as it passes through the point of constriction, isn't slamming up against the teeth, which for the sibilants generates an increased amplitude for that turbulent noise. So another thing about these different places of articulation, besides whether they're sibilant or non-sibilant, is that the articulators are moving into and out of position for those fricatives. They're moving from the vowel position into position for the fricative and out. And during that transition, that can sort of bend the formants briefly before we hit the actual fricative excitation, before the vocal folds stop vibrating into the voiceless sound or whatever. And so we get what's called a formant transition, and these are cues to place of articulation in the fricatives and in most other consonants. And then one last thing to point out about the fricatives is that in English, and in many other languages, but not all languages that have fricatives, we have a voicing contrast. So here's a fa and a va. And the main difference with voicing is that for the voiced consonant, we have a voicing bar. We see this band of energy at low frequency corresponding to the vibration of the vocal folds, where it's not seen in the voiceless sound. Also, because some of the energy, some of the airflow is being used to drive that vibration, there's not quite as much energy in the higher frequencies in the turbulent noise because the air isn't flowing quite as much. Some of that energy has already been taken away. Okay, so we have different places of articulation. We have the sibilant, non-sibilant, and we have that voicing contrast. The textbook introduces 4 spectral moments, which is kind of a colorful term for a collection of measures that are designed to quantify important elements of the spectrum of fricatives. We talked about some of the aspects of where the energy is concentrated. The actual values we get out of these measurements vary depending on recording conditions, and especially, as the textbook points out, according to sampling rate. So we don't yet have a generally agreed set of reference values to pin these spectral moments to. But it is worth knowing conceptually what center of gravity is, standard deviation, skewness, and kurtosis, because these are useful ways to frame our discussion around the shape of the spectrum. So do review that in the textbook. All right, in the next video I'm going to move on to plosives and other consonants.